Good morning, everyone. You can call me Cheah Wei. My full name is Leow Cheah Wei. I'm a director of Bymetrix Sdn. It's actually my own company that I set up with my partners. So I am from electronics engineering. I have the Bachelor of Engineering, Master in Engineering, and PhD, all from University Technology Malaysia. Back then, my research is in microelectromechanical system, MEMS. So after my postgraduate, I joined the company that gave me the scholarship. It was Agilent Technologies, now known as Keysight Technologies, producing things like oscilloscope, function generator. So I was the software engineers. That's why you can see my experience will be in modeling, in like software development, and also industrial automations. So before I set up my company, my last job was actually the technical manager for a company that sells MATLAB for 9 years. I'm still active in a society like Institution of Engineer Malaysia. I was the past chairman of the Electronics Engineering Technical Divisions for some time, and we are still active there. So that's roughly about me. So to save time, let's just directly go into the topics. Today, I'm going to talk about model-based developments in the context of digital twin and predictive maintenance. So this is a topic that is of my own interest as well, because I have been actually was the research leader for one of the fund that we get, crash funding, that we do together with a local university, as well as a multinational. So just roughly about my background, our company actually have presence in Malaysia, Singapore, Thailand, and Vietnam. Whereas Singapore and Malaysia having the same name, we actually sell a range of products. The first is actually a network simulator. Second is actually Altair, which is actually a finite element software, IoT, digital twins. Clockwork is actually used by industry to do code checking. And we also sell dashboard that actually let you do IoT. So just as a code of conduct, I actually want to stress that actually I also sell the software that partly I present today, but the topics that I present are generally still general purpose in nature. Okay. So today's what we're going to talk about model-based development, which is actually a philosophy about developments. And I will focus in the context of digital twin and predictive modeling, which is actually very relevant in the current IR 4.0 things. So in the industrial, this is actually a diagram that I actually got from internet. You can see that there are 9 pillars of technology advancements. So most of these things, I will save time, right? Like big data analytics, additive manufacturing, cybersecurity, in one way or another, is actually related to each other. So today I want to just focus on one of the topic, which is actually predictive modeling digital twin, that is related to cloud, related to the industrial Internet of Things, and it also related to the simulation and augmented reality, right? To some extent, it also is big data analytics, because the data may be hosted on your company networks. So feel free to actually stop me if I talk too fast, because the slide itself actually is 50 over pages. Some of the slide I will just go through. So actually I presented this topic before as well to some other crowd. So I actually just reusing it. So this is one of the funding that I got a few years ago. The research has been completed. We actually work together with USM and a German multinational in Penang in researching power tools. So you probably also can guess what is the company. And I was a research leader. So the topic is actually in producing a next generation's controller to actually control the motor of the power drill. So although I cannot actually speak in details on the research that we carry out, but I actually can tell about the background of the simulation flow. So what the model-based design that we adopt back then during the research is, presuming I'm using the Altair tools, right? The first level of modeling is always to come up with the mathematics modeling. I think many of us actually are using this in signal processing, in control system modeling like PID. So the mathematics can be done in the mathematics simulation environment. In Altair is actually the compose. Subsequently, we actually can go to the one-dimensional signal base, which is broad-based. right? It actually let you do a drag and drops and then build the signal in a with the time domain, whereas in the mathematics, you need to produce a time domain yourself. And in the one-dimensional simulator, you have the time domain built in. So it's very easy for you to model the system. And it also support like multi-physics. That means you can actually cross electric motors as well as thermal, maybe noise in the same domain. So after you do the modeling and simulation, you get the result that you want. You want to actually produce the code that actually can be programmed onto the board. So the technology nowadays is that as a can actually from this diagram automatically generate the C code. And we actually have a tools to actually do that. This tool can generate the C code to let you target to the controller. These tools can also be used to emulate hardware in the loop. That means, let's say you want to emulate a virtual motor that is responding in real time, so that you can test your controller, which is running in real time. You can do so. So the diagram over here actually show one of the setup that we have for the hardware in the loop setup in one of the Thailand university lab to do MRT model. So one important aspect in the tools that I carry nowadays is actually we can actually do very much digital twin. In this case, we are using the multi-body dynamics. If I play the video, you can see that you can actually model the car using finite elements, and you can see how it actually how the multiple parts interact with each other. In this case, it's the view going through a bumper. So this generally summarizes the workflow of model-based design. The benefit of this actually is it gives you faster development iterations because you can actually simulate before you actually come up with a prototype to test it. If you fail with the prototype, you got to spend a lot of time to actually fabricate it. It costs time and money. But for simulation, you can get it right in the simulation first before you actually go for prototype. And this is in fact what we use in my previous crash-funded research. And the other thing is that it's multidisciplinary, multi-physics. You can have like chemical engineer specialized in the battery cell lithium-ion working alongside with an electrical engineer that is doing the motor driver. It's also multi-physics in that measures. So another way to actually look at the model-based design rather than the flow that I showed you just now is actually look at this thing called the V diagram, right? So in this case, it actually show you, right, for a real product development in the company. For example, when I work in key site, we have the product and marketing team that define the product requirement, like your car have to, for example, your equipment need to be 10 gigahertz bandwidth kind of things. And from there, actually, the engineers or system architect will derive the system concept design by creating the blocks that interconnect to each other. And it might have multiple subsystems. For the example of the car, you might have actually like the topology optimization, the multi-body simulation. So all this actually help you to do the component in detail design. And eventually, we actually can simulate and do testing and system test integrations until you have the final product verification. Either you go through the hardware in the loop that I mentioned or not just now. And all this can be in a mechanical design, electrical and electronic design, and also the software design. Right? Okay. So this is very fast about model-based design. So in nowadays, the tools, although the tools that I actually carry is out there, but they're actually compatible tools out there that do pretty much the same thing. Nowadays, tools actually can do finite element simulation that enable structural stiffness simulation, like drop impact packaging, advanced material simulations, optimization. That means they actually can change the topology, change the shape of the device based on your input, and also can simulate the manufacturing like injection molding. And you can actually also do like CFD, computational fluid dynamics, which is actually used by multiple MNC. And you can do the system level simulation like control system. And even can do other domain things like electromagnetics. For my case back then is the motor design itself, right? So these are just, in terms of diagram, what are the different domain and applications. For example, in structural, you can do vibration, acoustic. So simulation tools nowadays can actually do cross-functional, multiple domain like this. And this diagram actually, this photo actually also show it to you. You can analyze the stress, you can analyze the computational fluid dynamic for the airflow. So all this you actually need to run on a backbone, like maybe it's a high performance computing, maybe it's on the cloud. So basically, most of the computer aided engineering nowadays actually offer this kind of seamless integrations, and we call this the simulation driven innovations. So I'll actually skip this slide. It's kind of repeat on what I briefed just now on the V diagram. So I hope you can look at this video. If there is no sound, maybe I would get back to you later. So in this case, it just show you like after you design your products, after you simulate it, when you deploy, how long, how fast is it for you to actually deploy it to a real system. So of course here it just show a Arduino, which is very simple. So that is uh, easy for academics to actually adopt to the syllabus, and also easy for even engineer to actually learn. So it takes about 1 minute, this video. If you cannot hear the sound, let me know later. But basically, you can also try to understand by looking at the video how from the diagram or simulation diagram can become the code. You can see here it's okay. Yeah. Yeah, just in case some of you cannot get or cannot listen to what it says. So basically, in a block-based development environment, assuming we already simulate at the system level, now we just want to deploy. So what it says here is actually we drag in certain block that actually generate the signal, certain block that actually convert the signal into data that is acceptable by the microcontroller. And there are actually blocks that represent the actual output that can be deployed onto the microcontroller, let's say an IO pin. And before you actually deploy, you can actually plot the graph to see the output, whether it is meeting your expectations. So if you go to the next step, which I'm going to continue the video, you see how it actually generates code and target to the block. In this case, it's actually doing a LED blinking, which is a very simple application. So I'll just complete it. It's in another 20 seconds. Yeah. Yeah, great. So I guess that will actually let you see, like from simulation to the deployment, actually is like a shorter way. Of course, if you do a complete system, you will have more complicated model and more complicated problem to solve. But generally, the workflow is the same. Okay, I'm gonna skip the other things. So in the case of like a bigger scale digital twin representations of the model, we actually can go through this microgrid case study, right? For example, in a microgrid, right, you may want to have some dashboard to actually visualize all the data. So of course, you can connect all this to the real hardware, but if you want to connect to real hardware, you need to set up a system which may be costly or difficult to achieve or difficult to model certain dangerous situations. So this is where actually we can use the hardware in the loop environment, which is actually using the things like low-cost microcontroller to emulate a plant or motor. So, and this is how it looks like. In this case, it's actually using up to 5 TI boards, which is actually the 28377. All these boards are interconnected to each other by using GPIO, SPI, CAN. So all these signal or data bus, just like the Arduino example I showed you just now, can be supported by tools like Embed. And all these boards, you can program in the behavior. Let's say I want to program a diesel generator emulator. I can emulate the diesel generator. I can also emulate all the wind spin the wind speed, the battery, and also the solar. In this case, it's because it's microgrid for solar, so it actually you can then simulate or emulate different situations. For example, I want the wind speed to be in certain speed that cannot be easily achieved with a real setup, in fact. And I want the battery state of charge to be in certain level. I want the fuel gauge to be certain level. So this is a benefit of actually using hardware in the loop. You can actually emulate the hardware system by using very low cost card and without risking, without doing dangerous thing, because everything is emulated and it's running in real time. So in this case, you are actually able to test your microcontroller or test your controller. Yeah, okay. So vSim here is actually the old name for Mbed. So basically, this is, yeah. So this is what we have in the actual case study for a lab that we set up in Thailand. So in this case, actually, you can see basically we can also use higher end hardware to actually emulate the entire system. In this case, it's an MRT drive, which is actually for a drive motor. I think I have the video as well. These are all the MRT motor. And this is roughly the setup. You have multiple stations and multiple of this motor all connected through a SCADA bus. And this is actually the entire block diagrams on the setup. And this is actually the video to let you take a look. You can actually emulate the signal onto all these test device. And these are the motor. Right. So this is actually where model-based design can be used. So some video I will show for other applications. Right. This is actually a system level simulation that you can actually also visualize. Nowadays, all this visualization can be interchanged with the word digital twin because it represents your robot arm digitally. So in this case, you can see the video arm with the robot arm, the virtual robot arm can move in accordance to your simulations. Right. So I have other video that actually showcase to you a range of possibilities that can be done by digital twin. So I'm going to skip some of this. This is the shape shaping optimization. That means if you originally have a design like this, you can actually use the simulation tools via the model-based design to actually optimize the topology or the shape. It actually will change for you. In this case, it's not done by human. All these changes is actually the software done for you. Okay. Right. For control system design, we actually have the tools to let you do the equivalent of PID controller or your control system. Provided you can actually model the system, you actually can use block like this to actually represent the plant response and also, in that case, design your controller. And you can further visualize everything. So I show the video again of a robot arm. In this case, not just a robot arm, it's actually taking a flexible device under test, not device under test, flexible things, flex it around. And in the simulation, we also show the stress that is actually experienced by that flexible device. So with this, the entire digital twins model of your system can be realized with a combination of the simulation tool and the visualization tools. Later, I will show you another example of how we actually do the things from scratch. So in short, in the model-based design, you can actually bring the one-dimensional block-based signal for which you are doing for system level simulation, for concept study, control system design, controller implementation, and optimize your performance. Can up to like looking at the 3D model, you can actually do what we call a core simulation with a 3D world to actually visualize the thing. I will have another example that actually show the concept clearer. So in the context of digital twin nowadays, this is what you maximally can use, right? You don't need to implement everything. So basically the core of this is actually the IoT, because your device actually, the physical asset will actually give you operational data, like how fast the motor moves, kind of things. And this will actually be fit into your IoT data intelligence system. You can make use of actually machine learning model, go through this IoT data intelligence to actually predict the potential failure of your physical asset. You can actually also use the 3D and 1D simulation that I showed you just now for the purpose of actually producing data that is difficult to achieve in real world. Let's say you want to predict failure of your robot arm. You don't want to wait until your robot arm fail to give you, then only it give you the operational data. You can actually model the robot and use simulation to make something fail and use this data in your model, in your machine learning model, right? So the whole purpose of actually doing this is like optimize product performance to derive operational insight and also to extend the product life. So I'm gonna skip some of these, right? These are some specific example on how to use sensor to achieve a model-based design to actually design a product. So in the case of predictive maintenance, the flow chart of doing it is actually you have your physical asset, you connect it to sensor data. Normally nowadays, many factories are starting to have all this data acquisition connected to what they call as dashboard. Dashboard is just visualization, and all this data you can actually do processing. You can also use the data to implement your own machine learning algorithm by combining other tools like Python, C++, machine learning, deep learning. Eventually, when you have this model, right, you can integrate it back to the IoT dashboard, and this whole system is basically like a flowchart. So this is like the flowchart of actually how to implement a digital twin, specifically predictive model, predictive maintenance using model-based design. This is another test setup that we physically set up right now is at HHRDC, the Selangor Human Resource Center. So it's actually a fan that actually blowing to a wind turbine. So what we does is actually we collect operational data. We actually purposely make some failure. We collect the data by making some screw loose or kicking some place. And to collect data, we actually use it to create a predictive model. And we actually can detect what failure might be happening to the wind turbine. So we actually use this as a showcase demo at the Selangor Human Resource Center. So the device that we put in is actually like strain gauge, accelerometer, and of course the wind turbine also produce voltage. So we have this, and we actually also have an optional accelerometer to actually collect the wind speed. So this is how the simulation looks like in 3D. In fact, this is using the Motion Soft, which is the multi-body simulator. That you can model the and visualize the stress that is inserted. So you can actually use this to actually as part of your machine learning model. So the other few slides, I will just roughly show you how the environment of this mathematics tool looks like. This actually is the environment that you can use to actually process the data, make from things like curve fitting all the way to integrate it with Python to do machine learning, right? So and for that particular demo that I showed you just now, these are the actual screen output. It actually show all the data. And this actually gives you an idea of the setup that you possibly can have for machine learning, all the things that is used. For example, under the classifications, under supervised learning, you can support SVM, KNN. Because of the fact that we can actually just run Python as it is, you don't need to actually recreate the view inside our simulator. You actually can just use Python to do it. So the rest are just, I would say, like different topics of the machine learning. So the machine learning topic itself is quite a big topic. We're not gonna go into details. So again, by utilizing this, to produce the prediction model, we can actually predict the remaining useful life of the device, right? So in this particular case, it shows the prediction in red color. So just now I talked about the model. So how do we actually implement this onto a real IoT system? So what we have covered earlier is actually we use embed to eventually we use compose, which is the mathematical environment to model mathematically. We use activate, which is a one-dimensional signal-based block. Then we actually deploy it to a microcontroller or your actual controller using embed. You can also use other finite element tools to actually do like structural simulation kind of thing. Eventually, you have your model. You want to actually implement it onto our IoT network. We actually support. We don't explicitly just support our own tools, but if under the Altair itself, we also have an IoT service, which is actually called Altair Smart Core. The way is for you to manage the data, and you can even visualize it using the Altair Smart Site. So it's like a cloud dashboard. But other than that, we also have other tools such as the Analyticon. We actually can do real-time streaming of very huge data, and some tools that actually can do machine learning with just without programming. And all this actually you can do. This digital twin technology can mimic the real-life condition, and actually can provide you a reliable real-time evaluation for the purpose of predictive maintenance. And this actually shows some sample output. If let's say this is your factory, you have sensor connected. Eventually, you have the Altair Smart Site as the dashboard. You can probably see output like this across the United States plants that you might have. Okay. Yeah, the rest I will skip because it's not model-based design. It's cybersecurity, but not a lot of it. But the key takeaway of it is actually today I share about model-based design as a design philosophy, and it can be used as a digital twin to do predictive maintenance. And the purpose of achieving all this, not just because it's like Industrial 4.0, it's actually things that a lot of companies around the world is actually adopting, because end of the day, it potentially can provide a good return of ROI. Right. So in the context of academic, other than this slide, I just want to show you something extra. This is actually a edu hardware kit that we actually use for teaching. Okay. Right. So with this, I want to go slightly deeper into the core simulation. So let's say you have the one-dimensional model. How do you actually run together with a 3D model? So the technology is using this thing called the FMI, right? So I'm gonna make this screen bigger. So this is actually called a functional mockup interface, which is actually an open standard adopted by many simulation tools provider, not just limited to Altair or few. In fact, even company like NC's, MATLAB also have this kind of interface. The purpose is for tools from different domains, such as like from thermal, from system level, to talk to another tools in other domain. So it can be across different company as well. So for example, if your university of your company maybe have NC's, you can actually use it to talk to the motion soft in Altair tools, because both of them actually support the functional mockup interface. So I'll just show you one more slide, like how it actually interface with each other. So for this FMI, it can actually do two main things. One is actually you can use it to do the model exchange by just sharing the model data from one tool to one another. Another deeper is actually to do FMI for core simulation. That means we can actually use one tool to the FMI, talk to another tools, get the solution, come back, and then do a loop. So this is the topics that I want to mention, in fact, for the core simulation. So let's just look at one diagram. So in the Activate tools, when I open Activate, I actually have this block that when I pull in, I can actually have this interface to let me define the FMU, which is actually the functional mockup unit that enable me to do FMI. So this is how actually you interface and talk to other tools. Everything is actually through a text interface. And I'm going to just use this diagram to illustrate. Let's say you have a block that actually have input 1, input 2, the sum and the product. In the block, it actually looks like this. And when we run the simulation, it actually will give us the core simulation result. Yeah, so maybe we take a look at this short video to actually understand the concept. So in this particular case, it's actually an inverted pendulum, right, in MotionSoft. So how do we actually achieve this core simulation with other tools? is actually we use Activate, which is in these tools, right? We actually can define the controller. In this case, it's using something like a finite state machine, and go through the motion soft block later on. So this controller internally will look like this, right? All the blocks, the plant. And this block will actually connect to the motion soft, which is actually a functional mockup interface that talk to another tools. And then this functional mockup interface tool is actually this 3D simulation multibody. So this, the rest is actually just the settings. After defining the proper settings, you can actually run the simulation and you can visualize the output. So in our education kit, yeah, actually we have come up with something which is just a linear stage. Let me just close this. This will be the last 10 minutes of my presentation. So we actually have created this linear stage. So basically, this is actually to show how you actually can do this kind of simulations, right? We actually use a typical CAD program to actually draw and export the model into the motion soft aspect file, and then we actually can right. Let me just skip to the portion. Right. So basically, we need to define two blocks. One is static, which is a green color. One is actually moving. We define the blocks, the points, or what we call actually the joints, and we also define the which body. We define the either we want to provide force input or we want to provide motion vector input, and then we can actually use an external program to actually provide all the stimulus. So in this case, we are using Activate. So let me just close this. I show you the model. Right, close this. So close this. Right. So show the model. Right. So this is how my model looks like in the control system portion. Okay. Give me some time to turn on. Yeah. So yeah, so as you can see, this is actually my functional mockup interface that actually points to some files that I have created right, in the multibody, and I drag in a signal generator to actually define the output value versus time as a vector, force vector. Then I can actually look at all this data. So, but what this core simulation does, it means this portion, I mean, except the center portion, everything is running in Activate. It's pass the data to the motion soft simulate and return it. So the end result is it after I do the simulation, right? I actually can load the model. Yeah, which I already previously run. The last time I ran was actually last night, so I don't want to rerun it just to save time. So this is actually the model. Because my input, as you can see, is having this time vector. If I visualize it, it will look something like this, right? In an X and Y sequence. Basically, it just go to some place and go back, go to some place. So you can actually see by playing the result. Okay, let me just open it again. Hands on. Force. This one. Right. Not sure why the video didn't pop up. Okay. Sorry about that. So by right, perfectly, you will see my stop playing as well. Okay, maybe I need to simulate one more time. Okay, for some reason, I'm sure. Okay, let me just define it again. Maybe change the file. Okay. Okay. Yeah, let me just simulate one more time. If it didn't show properly the video, we can temporarily forget about it. Right, let me just define the output. Uh, yeah, we can define it here. So I'm gonna apply it, override it, and I just run the simulation one more time. It actually doesn't take a lot of time, but because I want to save time, I don't want to just rerun it. So while it's simulating, it is just simulate and it finished. Then because I saved the output, so I will come back to here, make sure that I'm in hyperview, and I open the model. Right here. Yeah, okay, so it's just freshly simulated. As you can see, the time is 11:29. Right, okay. We just play one more time. So for some reason, I didn't see the video active mode. Let me just close it one more time. I think it will give up if it doesn't show it again. Hyperview. Yeah, let me just try to load one more time. Force. Okay. Oh, this one I need to set to view. Yeah, okay, so something is missing. Okay, I will skip this portion, but by right, you actually will see my model that actually look like this. Let me open the original model and look the order, the result again. Yeah, I think let me give out this. Maybe it's in the web conference. This cannot be rendered properly for some reason. But I think you should probably get the idea. This one I just showing in details actually how it actually run, and then you get the output in the 3D. So apology for the problem of this. So with this, actually, I want to end my presentation. Although we started a bit later than what we planned, but I tried to change time by presenting quite fast. So hopefully you can get the whole thing. So this actually showcase like actually how to actually use tools like CA nowadays computer manufacturing engineering to actually do a model-based design-based approach to actually do a simulation-based design that eventually can also target to hardware, and also you can visualize that at digital twin. So with this, I would actually end my presentation and we to the question and answer. Yeah. Thank you, everyone. Yeah. Again, thank you for attending. Yeah. Any question, feel free to actually contact me offline if you want. Okay. Thank you. Bye.